As Henrik already mentioned, there will be a contribution from one of his colleagues, which is Lasse Keppel-Mortensen, and he will also talk about fault detection and diagnosis based on sensoring data. Here you go.
Thank you. First of all, to those who aren't aware, district heating systems are systems where heat is produced at central or decentral plants, and then subsequently transported to consumers via distribution and sometimes a transmission network, and it can offer a cost-beneficial alternative to individual heating. In a global perspective, district heating accounts for 9% of the world's final heating demand for buildings and industry, and 86% of the primary energy for district heating is based on fossil fuels. This, of course, varies from between regions of the world, but it's a quite high amount. Now, faults in district heating systems, such as cracked or burst pipes, degraded insulation, or poor customer installations, they all decrease the energy efficiency of the system and potentially lead to water losses. Water losses that can be in the order of magnitude of several hundreds of thousands of cubic meters annually for medium-sized district heating networks. The current detection practices include thermal imaging, as Henrik also touched upon. You'll typically do sweeps of the network at regular intervals. You can do a full or partial sweep of the network every year using either drones or cars fitted with thermal cameras. The problem with this solution is there is some lag between the actual fault event and the detection. Other alternatives are flow monitoring, which requires some observability in the district heating network, and this is a common problem for district heating systems. We tend to have high observability of the central plants and also decentral stations, for both heating and pumping. And then the last layer, you can say, of monitoring is at the individual households, where the data is typically used for billing purposes only. Then there are also some lines of work that focus on identifying poor customer installations based on the data from heat meters of the individual households. But in this context, we propose a virtual sensor-based approach for fault detection and location, which has two main components. And these are virtual sensors, which are bottom-up flow aggregations, and a model of the network for simulation. In this approach, faults are detected as deviations between simulated operation and the virtual sensors. Now, if we look at the top right corner, the figure in the top right corner, we see a schematic of what I mean by virtual sensors. How we create them is that we start at each customer, then go in a direct path to the substation, grid-side substation, and we place a virtual meter point between each set of nodes. We do this for all consumers, and then we eliminate any duplicate virtual sensors. Now, these virtual sensors, they aggregate the flow of all consumers downstream of them. If we look to the lower right corner, we see a schematic of the proposed approach. We'll use the virtual sensors to automatically determine clusters of consumers and their relation in a hierarchical sense. And then starting at the topmost cluster, we will start our fault detection and location protocol, in which we'll use the simulated flow measurements and the flow measurements from the virtual sensors for comparison. The model, as Henrik also touched upon, is developed in a software called Lean Heat Network by Danfoss. It does hydraulic and thermal simulations based on defined material properties and boundary conditions at the substation and the individual consumers. It can connect with SCADA systems to import data in real time and automate calculations. In the scope of this paper, we used the measured supply temperature and return pressure at the substation and pressure change at a critical node in the system as boundary conditions for the substation, and for the individual consumers we use the return temperature and the heating demand. Now for the clusters. The objective of the clustering is to define clusters of consumers that are represented by nodes in the model and by virtual meter points, and they will naturally have some physical network location properties. We see a few schematics here. On the left side, you see a graph of the network in a small part of the network for only 7 consumers. These are the blue dots. On the right side, you'll see a dendrogram. The clustering approach we use is an agglomerative clustering approach, a bottom-up approach, you can say. We do a small modification to discard clusters which are not represented by a virtual meter point. And that's why we see that consumers 4 and 5, can I point with this? These consumers, they are clustered together, but the cluster that contains or could have contained consumers 4, 5, and 6, this as well, we discard as a cluster because we don't have a virtual meter point which aggregates information of only these 3 consumers. So we can't use it for our comparison. Yes. Then for the fault detection and location protocol, the network is searched in a top-down approach, starting at a cluster is defined by a distance threshold. So if we move back to the dendrogram, we could set the distance threshold at 120 meters. There is a trade-off for the distance threshold. If you start too low, you have to do a lot of computation. If you start too high, you might obscure some of the fault symptoms. But in this case, this is actually one of the case studies we're going to be looking at later. We would start with one cluster, potentially consisting of multiple subclusters downstream. If we detect a significant deviation between the simulated flow and the virtual flow meter, if we don't detect a significant deviation, then the clusters fall free. We move on. If we do detect a significant deviation, then the cluster is faulty and its downstream clusters are investigated individually. The case study is the same as Henrik explained earlier. Small part of a larger district heating network contains roughly 650 consumers. And the heat plant we see at the bottom here, it represents the transition from the transmission to the distribution grid, a pumping station. Case 1, which was the graph I showed earlier, in that we detect faults or a fault in cluster 1, so we see up here. Then the protocol tells us to look at the subclusters of cluster 1, and we see that subcluster 1.2 is fault-free. We have no significant deviations, but in subcluster 1.1 we have a significant deviation. We can then continue on and find in the end that the fault only affects one consumer in subcluster 1. In another case, you'll see an overview of the network in this small part. We detect a fault in cluster 2. When we do a subdivision of the cluster, we see that subcluster 2.1 is fault-free, while subcluster 2.3 is faulty, and the same for subcluster 2.2. When we go down further, we find that there are one consumer in subcluster 2.2 which experiences some abnormal behavior, and 3 out of 4 consumers in subcluster 2.3 that experience some normal behavior. This, aside from us narrowing down the location of the abnormal operation, we also get some indications for what potential problems could be. Could be a poorly insulated pipe, burst pipe, or something that is upstream from this cluster. Whereas if we only have a single consumer, cluster with a single consumer experiencing some abnormal behavior, then the problem is very likely local. For the limitations of this study, we sadly had no true labels initially, which means that a proper validation of the actual faults could not be done. Another thing is that our methodology and the clustering approach do not account for meshed connections. This is typically not a problem, as the district heating utilities, even though having mesh connections in their grid, will try to operate it radially and only use it for changing the topology. Yes. So in conclusion, we have a top-down fault location approach, which identifies abnormalities that are indicative of faults, and it provides locations to guide subsequent investigations of these faults. Thank you for your attention.
Thank you, Lasse. Are there any questions?
Thank you for a nice presentation. I was thinking this is maybe more question about the accuracy of lean heat.
Yeah.
But do you have any ground truth data, I mean, from this network, so you can actually compare whether the simulation done by lean heat actually match what is really happening in the distribution grid? Do Fjernvarme Fyn have any metering points where you somehow can cross-reference and see that it fits?
No, again, for this case study, and it goes back to the problem at hand that we have kind of low observability of district heating networks, so we don't have any measurements in between that we can use to verify the model. And I think it's also a problem that we are not sure that the network is operating fault-free. So even if we tune the model to our specific data, are we tuning it to an optimal operation, like a fault-free operation? Are we tuning it to actually represent the faulty scenario? And that's kind of a challenge or a dilemma in this sense.
More questions? Well, yeah, Grace?
Yes, maybe I just have one question. It's more like not so much familiar with this detailed fault detection in the district heating. So how frequent of this fault happens in district heating, and where it happens usually?
So I've worked with a couple of different data sets on district heating. Now, this district heating company that we're working with, they supply in total 100,000 consumers. And as Henrik touched upon, poor customer installations, low cooling efficiency is a very typical problem. And there are some lines of work that are dedicated to identifying these cases. Some of the other cases that I mentioned, for instance, thermal imaging, I used to detect, in a period over 3 years, detected 500 leakages or burst pipes in this network. So that kind of gives a grasp of the order of magnitude of the faults. Maybe one final note as well. For new district heating pipes, they are being installed with copper wires to do leak tests as kind of a reimbursement case for if the district heating pipes fails after only 5 years or something. Maybe it's something to do with the installation and the district heating company won't have to pay for that. But you use copper wires and some resistance testing to catch those cases. But I said I don't have any data for how often those occur.
All right, I think we have one more comment or question.
Yeah, I think, do we take into account if people are on holiday and so on? Because I think you have a lot of metadata, people who are on holiday or have closed it for some hours of the day, the temperature will just drop. So
yeah, I mean,
how did you take that in? Yeah.
Yeah, I mean, this should be represented in the data, because we use as boundary conditions to initialize the model data for the energy consumption at the individual households. So if they are not using any heat, that should be represented in the model. There is a case to be made that, and as Henrik also touched upon, this tool Lean Heat Network has some troubles simulating very low heat demands that can cause some numerical issues, and that's why you see a push of the boundary conditions in some cases.